Hey everyone, and welcome to this explainer. Today, we're diving headfirst into a real-world Python practical file. We're going to be taking you on a journey, starting from basic math scripts and working our way all the way up to advanced binary data storage. So if you've ever wanted to really understand how simple lines of code can evolve into permanent, complex data structures, you are in the exact right place. Let's get into it. Here's a quick look at our roadmap for today. We'll start with math algorithms, then move into Python recursion, tackle manipulating text, step it up to processing text files, and finally, we'll explore binary file storage. All right, let's jump right into part one, math algorithms in Python. We're kicking things off with some foundational computer science concepts. Take a look at how elegantly Python handles iterative math here. We've got a classic problem, calculating a factorial. The way it works is, Python takes a user input, let's say the number 6, and it sets up this simple while loop. As long as that number is greater than 1, the program continuously multiplies the running total by that number, decreasing it by 1 each cycle. It's just a perfect closed loop of logic.
And when we run it, the script perfectly retains that running total in active memory, dropping the final calculation right into the terminal. It gives us 720, instantly, without skipping a single beat. Now, let's see how this logic evolves when we need to figure out if a number is prime. You could just check every single number to see if it's a divisor, right? But actually, scratch that. This script imports Python's math module to find the square root instead. That's the real trick here, optimization. By only testing divisors up to the square root of your target number, you drastically reduce the number of loop iterations needed. So whether you type in 117 or 19, the code highly efficiently routes you to a true or false prime check. So, loops are absolutely fantastic for the kind of linear math we just saw. But what happens when a problem isn't a straight line? What happens when a problem requires a function to continuously refer back to itself just to find the answer? That brings us perfectly to section 2, unlocking Python recursion. Recursion is honestly kind of a mind-bending concept. It operates a lot like a set of Russian nesting dolls, opening one inside the other. In this list summing experiment, you'll notice there is no standard while or for loop doing the heavy lifting. Instead, the function literally calls itself from within its own code. It takes a list of elements, pulls out the last number, and then basically asks itself to add that number to a slightly smaller version of the exact same list. To put that into perspective visually, it breaks down like this. The code just keeps layering itself, suspending every single calculation in active memory. It keeps nesting deeper and deeper until it hits what we call the base case, which in this script is a list length of 0. Once it hits 0, it collapses all the way back up the chain, adding the numbers together to deliver the final sum of 210 for our 6 inputted elements. And we see the exact same elegant architecture in this script, which calculates the Fibonacci sequence. To find the 10th term, the program doesn't just count up normally, it recursively splits the problem into finding the 9th and 8th terms. Those then split into even smaller terms over and over until they hit the base cases of 1 or 0. Finally, the whole thing cascades back up to output 55. Okay, so far we've just been crunching numerical data. We've optimized loops, we've layered functions. But real-world programming usually involves parsing vast amounts of human language, not just integers. Which leads us to section 3, manipulating text and strings. We're moving from ephemeral math to searching through raw alphanumeric characters. If you need to find a specific word in an absolute sea of text, this string search script handles it beautifully. It takes a raw sentence and uses the .split method to break it all apart into a list of individual words. From there, it simply loops through that list, checking for exact matches against your target word, and increments a counter every single time it gets a hit. And as the output proves, this logic works flawlessly. Asking the script to find the word computer in our test phrase instantly returns an accurate count of 4. All right, let's take it a step further in section 4, processing text files. Manipulating a single line of inputted text is one thing, right? But processing entire saved documents introduces a whole new level of complexity. We are stepping up to true file handling here. We use the open commands to read a standard text file line by line. The code pulls the raw data in, splits it into words, and then dynamically appends a hash symbol to every single word before printing it back out. It's a really great example of modifying text on the fly as you read it right off a disk.
In the next experiment, the script essentially acts like a high-speed scanner. It reads the whole file as a giant string and utilizes built-in string methods, things like .isalphabet, .islower, and .isupper, to categorize and tally every single character into specific buckets. Vowels, consonants, capital letters, they all get sorted into this very tidy table format in the background. But there is a massive distinction we need to make here. There's a huge difference between reading a plain text file like a human would, parsing it character by character, and saving complex data states exactly how a computer reads them natively. And that brings us to the climax of our structural journey in Section 5, Advanced Binary File Storage. This is all about permanent, mutable data retention. In our final experiments, we aren't just saving flat words anymore. We're saving nested lists of student records. We pull this off by importing the pickle module. Pickling serializes Python objects directly to the hard drive in binary format. You just open a file in write binary mode, create your complex lists of roll numbers, names, and marks, and use pickle.dump to cement them permanently onto the drive. So let's see how this actually evolves into a real database system. By opening that student.dat file in binary read-write mode, the code can securely fetch a student by their specific roll number. It instantly retrieves the records for Jasbir and Amit, and then allows the user to directly update their marks right there on the file. This step is absolutely crucial because it answers the ultimate question of data persistence. What actually happens when you turn the computer off? With variables in active memory, they just vanish. But here, the pickles binary file ensures the data survives exactly as you left it. Being able to see Record Updated pop up on your screen means you have successfully bridged the gap between temporary active memory and permanent structural storage. Those updated marks are locked in binary format on your hard drive, totally ready for the next time the script is run. From basic factorial loops and mind-bending recursion, all the way to pickling binary databases, you can now see how these core fundamentals layer together to build incredibly powerful, persistent programs. So I want to leave you with this thought. If you can serialize a simple student record today, what complex data systems will you serialize next? Thanks so much for joining me on this explainer, and keep exploring.